Hello, everyone. Let's start the EuCAPT colloquium today. And it's a great pleasure to have our speaker, Dragan Huterer, who is a professor in the University of Michigan. And he's going to tell us about the cosmological results from the Dark Energy Spectroscopic Instrument. Let's welcome, and please start if you are ready.
Thank you, Jihang. Hi, everyone. Good to see everyone on Zoom. Can you see my screen and can you hear me? Jiban, can you?
Yes, I can see your
Okay.
screen and hear
Good.
you.
Thank you.
Yeah.
Thank you. Hello, everyone. It's a pleasure to speak here. I am Dragan Huterer. I am a cosmologist at University of Michigan. I will tell you about DESI results for people who are not cosmologists or who are just learning cosmology. I have some background through which I'll go briefly. For cosmologists, I'll have some of my own takes and trying to understand this, some really interesting results that DESI in combination with other data has obtained. Also, this is European Forum. I know some or many of you are part of Euclid. Um, our impression here in United States is that everyone in Europe is a part of Euclid, which is probably close to true. And I can't wait to see what results Euclid finds on dark energy, on the neutrino mass, and everything. That's going to be really, really interesting. So I will start by reviewing some energy. This, by the way, is the real picture of galaxies. We sit at the center. These are galaxies. It's a small fraction of galaxies collected by DESI, about 100,000. The color is fake, but their distribution in space is not. So just to start this background, from the Big Bang to the present day, many things happened. Accelerated expansion during inflation, then radiation, then matter dominates. But at late times, the universe is dominated by two components, dark matter and dark energy. And this talk is going to be about dark energy, mysterious component that was discovered about 25, 30 years ago, whose nature we still do not understand. This is a single slide in what could be a whole talk about the discovery of dark energy, which is a really fascinating story that starts many decades ago and continues through the 90s. But to make that long story very short, type 1a supernovae, a certain kind of explosions, that have very nearly the same intrinsic luminosity, that is to say, absolute magnitude. Cosmologists found ways to detect them and follow them up in the 1990s. That was a challenge. And then if you look at this physics equation, that flux and luminosity, you measure flux from a supernova and you don't know the luminosity, but you know it's the same luminosity for every supernova approximately. And then from that, you find not quite the luminosity distance, you find the ratios of luminosity distances of those supernovae because they know, they all share essentially the same luminosity. And what's important is a correction that's done along the way, which goes by the way a name broader is brighter. Brighter is broader. That is to say, the intrinsically more luminous supernovae, slightly more than the average, have a broader light curves. So once that was done, actually, this is one of my favorite plots. It's both popular and technical. So on the y-axis is the distance modulus, like log of distance as a function of redshift. And each data point is actually real data. It represents about 20 supernovae, so they are binned in redshift. And you can see these are representative curves of open, flat, and closed. There are many more, but this is just representative. You can see that neither one fits the data, but rather the one where universe accelerates now and decelerated in the past. And now it's not so simple here. Actually, all of these curves can move up and down, corresponding to the fact that we don't know the absolute magnitude, the intrinsic luminosity of a supernova. So you cannot say that these green curves are way off. You can slide them all up by a constant. So you really have to look at the shape of this Hubble diagram, the shape of distance versus redshift relation. And it's still true that neither of the green curves fits the shape, but rather there's something like the blue curve. So that leads to this picture drawn here in a very crude illustration where universe is decelerating, and then very late in the history of the universe, very, very late, about 5 billion years ago, so much after Big Bang, it starts to accelerate again. And the picture in which dark energy is about 3/4 of the energy content and dark matter is about 1/4, and there's a smaller amount of other components. And so the constraints on dark energy, again, to a cosmologist, these are very familiar. I'm going through them fairly briefly. Matter density and the y-axis is dark energy density. And the supernova data indicated that dark energy density is greater than zero. So it's the fact that blue curve is greater than zero on the y-axis that's won the Nobel Prize in physics in 2011. This was the discovery of dark energy. You cannot fit it with any model with matter only. This is supernova data. The green curve is by now an obsolete version of another probe that I'm going to talk about later in this talk. And then we often study equation of state P over rho of dark energy, which is equation of state is 0 for matter plus 1/3. So this is really P divided by rho C squared in MKS units, but we use natural units where C is equal to 1. And so W of -1 is a special value. Around that value is where the data is shrunk. And, at least as of some years ago, and actually even today, if you fit a constant W, you find it's very close to -1. P is equal to minus rho. That corresponds to energy of the vacuum. And later in the talk, I'm going to talk about parameterization of equation of state that allows it to vary with time or scale factor or redshift. And I will show some interesting results on that. Finally, to wrap up the background on dark energy, there are two famous mysteries with dark energy. One of them is why it's comparable to matter today. So here we are today when dark energy to dark matter is about 2 to 1. So they're comparable to each other. It's 70% to 30%. In the future, presumably dark energy will dominate. This behavior of dark energy, this is energy density as a function of time. It depends on the equation of state of dark energy, but for W -1, it's exactly flat here. And then matter and radiation are diluting with time. And in the past, we know for sure that matter and radiation dominated. This enables standard thermal history of the universe. So why we just happen to live in an era when the two are comparable rather than billion to 1 or 1 to trillion is considered by some people to be a mystery. It's hard to put a metric on this, how surprising this is, but it's considered to be. Many models have been attempted that try to explain this ballpark equality today naturally. Many models have been built. That's one of the two problems. And the second of the two problems is maybe one of the most famous problems in physics. If you calculate, so P is equal to minus rho, actually it's great. It corresponds to vacuum energy. But if you calculate the amount of the vacuum energy, and this is not quite the right calculation, but it's the one very often showed, you get a very widely divergent number that diverges with high K, with so small scales. And if you cut it off at some scale, you get the answers here in these two numbers that are much, much greater than the observed. Actually, it's a fun fact. We didn't need to leave. Did not need to wait for the 25 years ago to hear this. Wolfgang Pauli, almost 100 years ago, he knew about this problem, and he knew about this calculation, and he said if this calculation were true, the universe wouldn't even extend to the moon. That was Wolfgang Pauli's words. That means there would be so much energy density that universe would be so curved that it wouldn't expand to big size. It would have turned around in the Big Crunch. So this problem has been known for almost a century, and there is no known solution to this problem to date. Many models have been built for dark energy. Many, many, many papers on this going back to 1987 at least, arguably even earlier. But they're all fine-tuned. For example, scalar field called quintessence could be the dark energy. The problem is the mass of that scalar field needs to have interesting dynamics comparable to the only dimensionful scale in the universe today, which is a Hubble constant, which is 10 to the minus 33 electron volts in mass units, which is a much, much smaller mass than any known particle. So theoretical modeling for dark energy is really not gotten to a very successful start, it's fair to say. Unlike modeling for dark matter, which has lots of arguably compelling models, not so much for dark energy. So in summary, existence of dark energy has been fabulously well established to more than 100 sigma. For sure, something like dark energy is out there in the universe. And the measurements are really good. I'm going to show some really good ones later in the talk. But the theoretical explanations are lagging far behind. That's a summary of dark energy background. In a parallel interesting development, there's something called Hubble tension, and I saw that you had at least 2 EuCAPT talks on this recently. I'm going to summarize it in one slide. one kind of measurements, Hubble constant has been widely varying over the many decades, but it converged to about 70 kilometers per second per megaparsec in the early 90s with measurements from Hubble Space Telescope. Now, both of these numbers, two kinds of measurements today, about 70, one is 73, one is 67, except the error bars are so small that they very significantly differ from each other. And so the local measurements from the local, what's called a distance ladder, indicate 73 or so. And from Planck and EuCAPT and the CMB measurements, it's really, really well determined to about 67. And I'm going to show later a measurement from DESI that's independent from the CMB, and we'll see which category it falls in. I don't think it's going to be very surprising. This, in my mind, is the single most exciting development in the cosmology in the past 10 years, and it's surprisingly hard to build theoretical models to explain this Hubble tension. It has to be one number. Hubble constant cannot be two numbers, and if it looks like it's two numbers, then maybe we need modification of the standard cosmological model. So that's why people are so excited about this. So now I'm shifting gears. I'm going to talk about cosmological measurements. And here I'm listing only the very best known international telescopes specifically targeted to go after dark energy. These are just the best known ones. There are many more. Euclid is here and Roman and LSST is here somewhere. But I'm going to talk about DESI. And I know many of you have seen talks on DESI. So again, at a fairly brisk pace, I will go describing what I think are the most interesting components. I won't describe the whole instrument and everything. And then in order to leave time to discuss its results. DESI is based on Kitt Peak, which is a mountain peak in Arizona. It's a Mayal telescope. It's specifically built for dark energy. Now, my observer friends, I'm a theorist, so my observer friends tell me that the telescope is okay. The telescope was built in 1972, the same year I was born. So telescope is not very young, exactly. And both the telescope and what makes it and the mountain peak is okay. I think Kitt Peak is nice, but it's not the world's best observing site. What is world-class here is instrumentation that was put on DESI. That's what my colleagues tell me. And in particular, it's able to get up to 100,000 spectra per night. Now, my career doesn't go back into the 80s when, people would go to the cold mountain and collect the spectrum. But when I was in graduate school and maybe a postdoc, I remember that Sloan Digital Sky Survey collected 1 million spectra, and that was a big deal. We have 1 million spectra. DESI gets 1 million spectra in 10 good nights of observing. And in fact, in the first 2 months, it exceeded all the spectra ever taken by humanity, just in the first 2 months of operation. So it's really a machine to get many spectra. And this is the DESI telescope, Mayal telescope, and there are lots of important parts that are important technological developments that enable this really exciting science. But the one I'm going to focus on was University of Michigan's claim to fame. This is fiber positioners. They're little sticks the size of a pencil. There are 5,000 of them, and there's a movie here showing what they do. And then they each take a spectrum of a galaxy. They each point to a galaxy, so you have to prearrange where the galaxies are. You take the spectrum, and then they move to a new position. They make sure they don't collide with each other. Then they each take a new spectrum, 5,000 spectra, and 5,000 by 5,000, they get to up to 100,000 in a night. This was built by Professor Greg Tarle and research scientist Mike Shubnell and their group. This was literally 3 doors down from my office at University of Michigan. And this is really one of the key components that enables DESI science, these fiber positioners that are collecting 5,000 spectra at a time. For us cosmologists, I think there are probably a lot of cosmologists on this call, but we are, they are test particles. Galaxies are our test particles. So if you have 1 galaxy or 10 galaxies or even 1,000 galaxies, that's nice. And, if you're astrophysicist, you can study them. But for cosmology, that's not so useful. But if you have millions of galaxies, then you're able to study their structure. And you study this filamentary structure statistically, and you discover wonderful things about our universe. And in particular, we use different kinds of galaxies. They don't have very imaginative names. At low redshift, this is the so-called bright galaxies, a bright galaxy survey. Then we have luminous red galaxies, another kind of galaxy with different spectral features that are older. We have emission light galaxies, They are younger galaxies. And then we have quasars, which are not really galaxies. They're quasars. And then we have something called Lyman alpha tracers, which is a altogether different kind of beast. So we have lots of apples and oranges, different kinds of objects, and we use them all in order to find out the science. And if you are not a cosmologist, or if you're just learning cosmology, this is kind of a useful graph. It shows a spectrum and how it evolves in time. So the vertical axis is looking back, going to higher redshift or looking back in time. And these are different kind of tracers that we use that I just described. And you can see a certain spectral feature. You find it at different wavelengths depending on when it was emitted. So by measuring a known spectral feature and noting the wavelength, you can tell the redshift at which that was. And using a cosmological model, you can infer the time, but you really get the redshift. Now, the sample on which these results are based is so-called DR2 sample. DR2 is 3 years of observation, so first 3 years of data from DESI. And you can see between DR1, which was 1 year, to DR2, there's a really very big jump in number, more than the double the number of total sources. So we have, I think, something like 50 million galaxies, but we only use 14 million that passed our, some tests. And we use that sample. And this graph is going to show the dark, this is where we look. Dark red is that you observed, and this is DR1. And now I'm going to click a button. As you go from DR1 to DR2, you will see the dark red will expand a lot. So we cover a lot more area in DR2, a lot more than we did in DR1. And we are really filling in these areas covered. Okay, well, so I was moving at a brisk pace. Next up, I would, there are hundreds of papers coming out of DESI. You see them on the archive every other day. They're on all kinds of things. And there are many things even within cosmological parameters, but there is one golden child here, one, one preferred child, one which is this baryon acoustic oscillations and BAO. That is the single most essential application. And if you're a cosmologist, you know this, and this is easy. If you're not a cosmologist, this is kind of a bit technical. So I'm going to spend the next 4 or 5 slides just briefly reviewing what BAO is. And BAO is, if you look at the power spectrum of matter, this is the power spectrum going from large scales to small scales, and this is linear, and then you have nonlinearities. You can see barely perceptible. So the power spectrum has almost all information. On linear scales, it literally has all information about the density field of, say, galaxies. And there are lots of features in the power spectrum. They can all be explained with cosmology, but the one we are paying attention to is these very slight wiggles. You can barely see them by eye. In fact, the dashed curve doesn't even have them. It's a fitting formula. It doesn't have the wiggles. You can see these wiggles. And if you zoom into these wiggles, you zoom in and they look like this. This is wiggles and this is some old data. This is not DESI data. Now, multiple wiggles in Fourier space, not surprisingly, correspond to a single wiggle in configuration space. So in real space, there's a single wiggle at about 150 megaparsecs or 100 H inverse megaparsecs. And this was first discussed by Sunaev Zeldovich. So this wiggle is excess probability for clustering for galaxy pairs that are about 150 megaparsecs away. So if you have if you're a galaxy 150 megaparsecs away from you, there's a 10% excess probability for finding another galaxy. Now, let's talk about why this wiggle why takes place. And it has to do with propagation of sound from the Big Bang to the present day. So sound, I think of as like a pressure perturbation. And if you think about that perturbation starting at the Big Bang and expanding, it goes with the speed close to the speed of light, c divided by square root of 3. But at recombination, the speed of sound drops dramatically. So I think this is the only formula I'm going to show today. And I just want to show that this formula is so simple that this is a few lines of computer code in Python. So, anyone can calculate this. So the distance that the sound travels is c divided by square root of 3. So as I said, speed of sound, which is speed of light divided by square root of 3 times time. This expression is time. And this first term is dt. And then there's a correction for baryons. Now, this speed that's very large, like I said, it drops like a rocket recombination. And so all of this distance really accrues between the Big Bang and about 300,000 years after the Big Bang, about recombination. And so if you calculate that distance in the standard cosmological model with the standard parameters, dark energy and dark matter, it's about 150 megaparsecs. So this is the feature that's being imprinted on the sky. And so we don't really see circles on the sky, but this is a really exaggerated artist's interpretation. Around each galaxy, you think about having an excess probability of finding a galaxy. And if you put all those rings around each galaxy, or really spheres in 3D, you find the density field that is imprinted. And because we look at galaxies on the sky, this is us, we're observing this feature, the sound horizon, that's 150 megaparsecs or so, at the distance to those galaxies. So we are really measuring this angle, the typical separation for this excess of clustering. So really what comes out of the box when we do BAO is this sound horizon RD divided by the distance. That's without any prior, with just DESI data, no prior whatsoever, you get the ratio of the sound horizon and the distance. And in a little more detail, and I'm not in front of you now to wave my hands, and I don't know, waving in front of the screen is not so helpful, but you can look perpendicular to the line of sight like drawn in this figure, or you can look at galaxy pairs parallel to the line of sight. You can also have them at an angle, but then you can project to one or the other. So you get two kinds of distances. You get this ratio, you get the distance to galaxies parallel and perpendicular to the line of sight. And sometimes we orthogonalize that basis and we talk about isotropic distance, which is a suitable product of the parallel and perpendicular distances. So this is like a perpendicular distance, and this would be like a parallel distance. And then you get the ratio of the two. And so you get two kinds of, you don't get one kind of distance, you kind of get two kind of distances. For each population of galaxies, you don't compress into one distance, you get two distances. The reason these two distances are important is that the formulae in cosmology are different for them. So there's a different theoretical formula for the parallel and perpendicular distance. And so you measure different quantities and really different combinations of dark energy parameters if you can get access to both of these distances. So that's what we measure. The distance, modulo some prior, like from Big Bang nucleosynthesis, to solve for the sound horizon, you can get the distance. Otherwise, with no prior, you just get this ratio. So this is now the kind of data separation. So first of all, let me show. So these are different tracers. And this is bright galaxies, luminous red galaxies in 3 redshift bands, emission line galaxies in 2 redshift bands, quasars, and then some weird combinations of the two. And then what you have there are 2 panels. The top panel is the power spectrum in configuration space with that BAO bump. The bottom panel is the so-called quadrupole. So there is also a quadrupolar component that goes as cosine squared to this. That's another story. It has less signal to noise. Let's ignore it for the moment, but we use that as well. But in the monopole, at least in the top panels, you can see the data are so clear that in each plot, without even the theoretical curve to guide your eye, you can recognize the BAO peak. So this is a very high signal to noise detection of the BAO peak. And you can see this is a kind of data compression. So you go from, what did I say, 14.2 million galaxies to what appears to be a couple of hundred data points here. And then from those couple of data points, after validation tests, we use these in the analysis. You use 7, there are 7 circles here. So you use 7 measurements of distance, but not really 7 but 14, because remember, for each tracer, we have parallel and perpendicular to the line of sight. So you go from 14 million galaxies to several hundred power spectrum measurements to 14 distances. And those 14 distances represent faithfully the dark energy data. And then those 14 distances we will we will convert them into dark energy parameters. These circles is what we used. So there's a very long and painful and essential validation paper, Andrade et al., that I'm going to mention also in a moment, that goes through many, many tests with simulations and some with real data still blinded, and decides that these are the safe combinations to use. In particular, for example, sometimes in one redshift bin, there's overlapping luminous red galaxies, emission line galaxies. We use the combination of the two. And so this is a result of validation tests done before we've seen the real results to decide what we can trust the most. In my research group at University of Michigan, Everybody has been in some shape or form working on DESI over the past few years. I'm here showing some essential people. And some of them really did heavy lifting. Ottavio Alves built the covariance matrix in Fourier space. Sikandar Hanif modeled fiber assignment. But I especially wanted Johannes Lange is a professor at American University now. He works on cosmology, also DESI. But Wendert Andrade, I'd like to highlight, he led this validation effort that I mentioned, the effort that decided what and where we can use for the cosmology analysis. So I'm going to talk about these now DR2 results from this key paper, and I'm going to show some of my commentary on it when I'm done. Also, validation, like I said, the really hard work was in this Andrade paper. And then in comparison, in my opinion, cosmology analysis is for the BAO is fairly straightforward. As far as things go in cosmology, for those of you who work on Euclid, weak cleansing and full shape galaxy clustering from the full power spectrum is a lot more complicated to model, to measure, and especially to model and to understand. And so in comparison, BAO is really fairly straightforward. It's very clean. That's the word on the street, and that's a conclusion I also came working on this. So I'm going to show 3 featured results, and then I'm going to show some commentary. The first featured result is the Hubble constant measurement, for which we only need, it turns out we only need the BBN prior on omega BH squared. So we need the baryon density to basically solve for the sun horizon. And from DESI alone and nothing else but BBN prior, we can get Hubble constant. And not surprisingly, we find a low value. We find 68.5 plus minus a very tight. This was fully expected. It would have been a huge surprise to find, 73 for this. All global measurements at z greater than 0.1, they all indicate lower value for the Hubble constant, and we do as well. So the nice thing here is without CMB whatsoever, not that you'd have a reason to doubt CMB, it's the single, maybe safest, maybe certainly most famous cosmological probe. But just in case anyone is, without CMB whatsoever, we find 4.5 sigma discrepancy with Schu's measurements at low Z. It's actually interesting that we find 68.5, not 67.5. You can see here that CMB finds 67 and we find 68. And that's interesting of a very mild discrepancy that's not statistically significant. But big picture, we find low H not exactly as expected. That's the featured result number 1. Featured result number 2, neutrino mass. I saw that in EuCAPT, you had several neutrino talks, neutrino particle physics in particular, and neutrino oscillation measurements tell us that there are 2 values of delta m squared, the differences of the squares of the neutrino masses, mass eigenstates of 10 to the minus 5 and 10 to the minus 3. You cannot solve the sum of the neutrino masses, but assuming the lightest one is massless, the least you can possibly get is 0.06 or 0.10 eV or so in the normal and inverted hierarchy. So the absolute minimum you can get for the sum of neutrino masses, it is about 0.06 eV in the standard cosmological model. Okay, this is a known material from textbooks. Now, it turns out, perhaps surprisingly, and I learned about this late in life, neutrinos, even though we think of them as ultimate relativistic particles, they're actually non-relativistic today. Their mass is low, but the temperature of the universe is even lower today. Universe is really, really cold. So actually today, they behave like matter. They are non-relativistic. They contribute literally to omega matter. So omega matter is made up of dark matter, of baryons, and actually of neutrinos. And so the constraint on neutrino mass looks like this. The vertical axis is neutrino mass, horizontal axis is omega matter, just to show the degeneracy. We heavily rely on the CMB measurements. This is Planck plus EuCAPT that have this kind of degeneracy in this plane. And we at DESI, with, I think, a little bit of a prior, I think we need omega BH squared prior as usual. We constrain omega matter very well. And we actually constrain omega matter very slightly lower than CMB prefers. And so the intersection of these vertical contours by DESI and the slanted contours by the CMBs, the combined DESI plus CMB constraint, because we measure omega matter slightly lower, you can see that our vertical contour cuts off the CMB contour at a very sharp angle. So because of that, in part, we get this very, very tight upper limit on the sum of the neutrino masses, 0.064. Had we gotten a larger omega matter, this limit still would have been tight, but not nearly as tight. But because we favor low omega matter, we get this tight limit. This is in lambda CDM. If you think we should relax this to another model, then this becomes quite a bit looser, but it's still a tight limit on the neutrino mass. It's still low, but this is extremely low for this reason. I've heard some people say that, well, it's the omega matter is the culprit. Sure, it's hard to say what the chicken and what the egg is here, because sure, you can blame it on low omega matter, but it's actually, if neutrino mass is really this low, then you would exactly expect this to happen, the omega matter to be slightly lower than expected by Planck. So this we interpret as a signature that neutrino mass is very, very low. So here's how low. Here's the same kind of result. These are the different posteriors, the neutrino mass. This is probability as a function of neutrino mass. It doesn't matter too much what CMB you do. This is in lambda CDM. The dashed contour shows a much weaker limit in W0WA model. And these are the ranges by inverted and normal hierarchy. So we are bringing these hierarchies under some tension. There is no real tension yet, and that's all being examined in this Albers paper, contributed paper on neutrinos. But this has invoked some hand-wringing in the community. Some people are a little uncomfortable, even talk about negative neutrino mass, something I don't understand personally, because it cannot be negative, it has to be positive. But we allow for healthy, positive neutrino mass, including neutrino mass consistent with, I think, both hierarchies. But it's definitely starting to push in that limit. It's starting to push against theoretical predictions in the lambda CDM model. The last result I'm going to show is dark energy, and this has been widely discussed in the community. I'm going to briefly show the result, and then I'm going to tell you some of my opinions and what I don't know what's going on, but at least some facts that I know are true. So this is the widely discussed modeling of the equation of state of dark energy that allows dynamics. This allows variation in time of dark energy. A lot of people who don't work in the field ask, why did you assume this? Why didn't you not assume some other expansion? People have tried many other possibilities, and some of them are in contributing paper by Desi and in many other papers, but this one turns out to be very effective in terms of modeling real models and having few enough parameters, and it's really just right. So this is indeed the preferred description of variation of dark energy. And this is the W0WA space, where this is the standard cosmological model of W minus 1 in this point. And these are the DR1 and now DR2 constraints. Now, if you don't work in this corner of cosmology, just trust me on the fact that this is an extremely challenging parameter space to constrain. So these two parameters have a lot of degeneracy. It's really hard. Sometimes you see forecasted contours in this space that are very small, but that's forecast. That's kind of made up by definition. It's really very hard. There's a lot of degeneracy. So when we unblinded DR1 originally in 2024, and when we got these dashed contours, I was really excited, because the fact that they are not infinite, that they close and that they constrain one direction really well was very exciting to me. That told me that the data is really strong, this DESI BAO data. And then with DR2, it's even stronger. So you can see in this very challenging parameter space. This is, of course, marginalized over all the other parameters. Then now when you add CMB, you get the first puzzle here. So DESI plus CMB without anything else, no other prior, is about 3.1 sigma away from the standard cosmological model in DR2. And then when you add supernova datasets, you have a choice of 3, Pantheon or Union on the Dark Energy Survey year 5. And depending on which supernova dataset, you get slightly different result. In each case, you're away from the standard cosmological model. And you cannot combine the three sets because they are highly overlapping and it's completely non-trivial to combine them. So you must think about them either one at a time. And depending on which one you combine with, you get 2.8 or 3.8 or 4.2 sigma departure from the standard cosmological model. Now, we were very careful not to call this evidence, certainly not to call it discovery, nothing like that. One has to be very cautious here, but at least personally, I get excited at the 3.0 sigma level. 3 sigma is when I get excited. And this was great to get excited that there's maybe something going on in the dark energy sector that departs from W equal to -1. Before I discuss this, let me say a few corollaries. First of all, this, not as widely shown, was a very interesting development that went at once. So this departure, instead of combining with CMB, again, not that you would doubt CMB for any reason, but instead of combining with CMB, you can combine DESI data with Dark Energy Surveys 3x2 analysis. And I know this is a very annoying name. This stands for 3 2-point correlation function. So this is galaxy clustering combined with weak lensing and then combined with galaxy-galaxy lensing. So this is basically galaxy clustering and weak lensing from Dark Energy Survey. And then with or without type 1a supernovae. And with is orange, without is blue. But in both of these cases and no CMB whatsoever, you get something like 2 or 3 sigma departure from the standard model. So this is in the direction of robustness with respect to the data set. And so we really thought these are tantalizing hints of departure from lambda CDM. In terms of, so I showed some robustness with respect to data. In terms of robustness with respect to parametrization, so here's the W of Z, the equation of state as a function of redshift that was predicted by the best fit W0 WA model. So this model has two free parameters, W0 WA, and it indicates this green curve and the so-called phantom crossing, which is the fact that the phantom region is region for W less than -1. And to test someone's age, I can ask you whether you know why it's called phantom. If anyone cares at the end, I can say it's a funny historical accident. But this is the phantom region, and this is the kind of the non-phantom W greater than -1. And this is the best fit model. Now, people ask, and often people not working in the field, have you, what about other parameterizations? And we and others have tried many, and this Loda et al. Contributed paper tried many, many other parameterizations, Gaussian processes, all kinds of things, and you qualitatively get the same result. And here's an example. This is just a simple bin parameterization of W. The error bars are much bigger, so evidence for anything is necessarily weaker, and there are 4 free parameters here. But you can see they trace out the same kind of thing as the green contour does. So this is typically the kind of result you get. You get qualitatively the same finding with other parameterizations. This one, we and others think is most effective, but you get similar kind of thing. And it indicates, at least at face value, that the raw dark energy increased with time and then decreased for these two behaviors. So this is kind of a popular level plot that I produced for some, I think, some magazine. So in redshift or in time, and so you can see if you run in time, dark energy density in this best fit model was increasing and then decreasing, sorry, as opposed to just being constant. And so this is such a bizarre behavior that I've heard some theorists say that this must be wrong. And I agree with their sentiment. This is so crazy. Would Mother Nature really do this? That dark energy first increases, which is weird, and then changes its mind a few billion years ago and turns around. That's really, really bizarre. Best fit model. But my opinion on this is to declare ruling out of lambda CDM, we should require we need like 8 or 10 sigma evidence to have a paper with a word discovery in the title. You know, this has to be very high bar. And I agree with people who are, suspicious of this. Yes, we should remain suspicious of this data until there's overwhelming evidence. Okay, we need a really, really high bar here to claim discovery of departure from lambda CDM model. That would be tremendous development. At the same time, these hints are really interesting, and at the very least, the minimum that they indicate is some inconsistencies. We don't know which inconsistencies. We think everything is consistent, but time will tell. So in the remaining few minutes, I'm going to show some quote unquote news, some different material about 5 facts and opinions about dynamical dark energy. These are things that are not like mathematical theorems, but they are almost certainly true. And I'm gonna tell you about these 5 things, and that helps at least my thinking about what's going on with dark energy. Okay, so I'm gonna go 1 to 5 now, in no particular order. So fact number 1. This is what makes us quite excited about these results. The preference for this departure or preference for W0WA evolving dark energy model doesn't come from a single cosmological probe. And just take a look at this table in our key paper. If you combine DESI with CMB, you get 3.1 sigma. If instead you combine with supernovae, you get 3.3 sigma. If instead you combine it with dark energy survey, galaxy clustering analysis, and lensing, you get 2.2 sigma. Okay, that's weaker, but that's just those two. And then even if you don't do DESI at all, not shown here, if you do supernovae only from Dark Energy Survey, this set alone, you get something like more than 2 sigma with no DESI at all. So it's hard to count how many independent pieces of evidence, but there's more than one independent piece of evidence that's hinting at these results. And that to me is quite exciting. That's fact number one. Fact number two, question, is there evidence in the data for phantom dark energy? So is there evidence that W is less than -1, like you see in the best fit model it is? Or is there evidence for phantom crossing? Or is there, some news articles had slowdown of dark energy, that's this region slowdown? The answer is no. So all we have statistical significance of 3 to 4 sigma is departure from the standard model, so departure from W equal to -1. But these independent pieces, slowdown or phantom or crossing, will necessarily be statistically weaker. We haven't quantified them. It would require a separate publication, separate effort to quantify them. It shouldn't be so hard. But for sure, it's going to be like 1 sigma or, 2 sigma at most. It'll be weaker, right? So that's why some people quickly wrote scalar field papers where show the scalar field that has W strictly greater than -1. It fits the data okay. It's not a great fit to the data, but it fits the data okay. And that makes sense because the evidence for phantom crossing isn't super strong. It's really just evidence for departure from the standard model that is fairly strong, 3 to 4 sigma. Okay, that's fact number two. Fact number three, and this is my favorite, and this is potentially the best insight we have to offer at this point. People ask what in the data is pointing at this dynamical dark energy, and that's kind of hard to pinpoint. But we got close in a couple of really, really busy plots we made in the DESI paper. And Arnaud Dematia made a much more user-friendly plot that I'm going to show here. So this is a much simplified version of a very busy plots we had in the paper. It's showing the following quantities. On the left, we have this isotropic distance, so one kind of distance as a function of redshift. And in each case, flat line is lambda CDM. So this is all normalized to best fit lambda CDM. In the middle panel is the ratio of the two distances. So just think of it as a different distance quantity as a function of redshift. And on the right panel is supernova magnitude. So this is supernova, again, kind of distance as a function of redshift. In each case, lambda CDM is flat and data is data. So, and the red curve is best fit W0, WA. So now you have to see what in the data is favoring red curve over horizontal unity or zero curves. And this is the so-called curvature in the data. So it's up, down, up. So up at high redshift and down in intermediate redshift and then at low redshift again up. So it's kind of, we call it, quote unquote curvature in the data. Why that is, we don't know. But this kind of curvature in the data favors W0, WA over either lambda or W. So even constant W does not have enough freedom to curve in these graphs to go up and down and up, which is why constant W is close to -1 and not a great fit. And this is why we prefer W0, WA so much. That has enough freedom to describe the data. Also not shown in this graph is a CMB prior. And so by eye, maybe you're not convinced why red curve should be favored to the black curve, but you have to trust us when you add the CMB, which is not shown in these graphs, that the red curve is favored by 4 sigma in this particular case over the horizontal curve. So this is one insight that is curvature in the data. Why curvature in the data, we don't know. But that might be a promising direction to explore in the future, why that is. Okay, so that's factor number 3. Number 4, as far as I know, there's no relationship between Hubble tension and this evidence for evolving dark energy. Both are kinds of tension. It'd be great to have one explanation for them, but that doesn't appear to be the case. And here's a simple way to see it. In the W0, WA model that now fits the data very well, Hubble tension is made even worse. Hubble constant goes from 67 to lower values with maybe a slightly larger error bar. And I haven't looked in terms of sigmas, it certainly doesn't help the Hubble tension. So Hubble tension doesn't get any better in the W. So as far as I can tell, Hubble tension and evidence for dynamical dark energy are independent of each other. It remains to be seen if they are related in the future, but right now we think they're independent. And the fact number five is that it's near impossible to relax both Hubble tension and evidence with the low-Z model. So this goes hand in hand with what I said previously, but imagine how you'd like to fit the data along with the local measurements of the Hubble parameter, because in DESI paper, we don't use the Shoes measurement of the Hubble constant. It's inconsistent with everything else. So when the data sets are inconsistent, you don't use them. So we didn't use that. Let's say now you say, I'd like to use Shoes measurements of the Hubble constant and DESI data and CMB. Can I make any model to fit the data? Any model? The answer is at low redshift, no. And so this is an illustration, and a couple of other teams wrote papers about this already. This is not a new fact. It's known among the experts. I don't imagine it's known widely, but we are trying, my student Prakar Bansal and I are working to clarify this. And here's a good way to look at it. This is the distance, distance modulus relative to lambda CDM as a function of redshift. Black is the best fit lambda CDM model. Black points are DESI points, and the supernova points are a little bit more complicated. These are the supernova measurements along with the anchor here from Cepheid. So this is the absolute magnitude distance from Cepheid. This is what anchors the Hubble diagram. This is the Shoes measurement of effectively the Hubble constant. So first of all, notice that the dark red and the black points are completely inconsistent because over the same redshift range, they differ by a lot. So you can't have a model at low redshift. You would have to fit data like have a function with two different values at the same redshift. That's impossible. Now, you could shift the supernova data up. Remember, I mentioned that supernova data magnitude can vary, but then you'd have to break this Shoes measurement. This is the Shoes measurement of the Hubble constant. So you would effectively have to introduce, if you moved supernova measurements to these faint values to agree with BAO, then this point would actually stay here. It shouldn't be plotted there. So then you would have a break in the Hubble diagram of supernovae. Then you would say that Shoes is explicitly the basically absolute magnitude of supernova changes from this value to this value at redshift of 0.01 or something, which nobody thinks is plausible. So there's simply no way at all to shift all the data at low redshift if you insist including the Shoes measurements. If you throw away the Shoes measurements, which we and others do, then of course you can fit data very well with a W0WA model. So this is an interesting fact shows the profound difficulty that this Hubble tension presents when fitting cosmological data. In conclusion, dark energy is a premier mystery in physics and cosmology today. We don't understand why universe is accelerating. There's impressive series of new measurements that are coming. Like particle physicists, we are really hoping for bump in the data and Hubble tension, and now evolving dark energy present that bump in the data that hopefully tells us something about the universe. Three featured results I presented: Hubble constant, neutrino mass, and dark energy. And much more data coming from DESI, soon from Euclid, I hope, from other instruments. But if dark energy anomaly is true, then we should be seeing it 5 sigma from DESI and combination of other surveys. We should have 5 sigma soon if it's really a true signal. That's all I have for today. I can take any questions now. Thank you.
Thank you very much for the fantastic and very exciting talk. Is there any questions from the audience? Please raise your hand or just unmute yourself. So maybe I have questions. So in the last fact you mentioned, what do you mean that it's nearly impossible? So does it based on the W0WA models, or I mean nearly impossible?
Yeah. Glad you asked because this came up quickly. So the statement is that so the starting point is you like to fit Shoes with other data, right? That's a starting point. If you don't want Shoes, you can have a great fit with W. But now let's say Shoes is inconsistent. But here's naive thinking. Naive thinking, well, Shoes is low Z, very low Z, and everything is high Z. So if I just make up a jump, in the Hubble diagram, I can fit the data. The answer is no, you cannot. It's a little bit more subtle than jump. No jump, even a made-up jump by pencil, can do it. And it requires a little bit of thinking. Why? It has to do that the shoes measures absolute magnitude. You need a jump in absolute magnitude of supernova. But if you just have jump in expansion history, like scalar field with some big oscillation or something, that cannot fit a low Z. So that only leaves these options. Either jump in absolute magnitude, so absolute, the luminosity of supernova changes 150 million years ago when dinosaurs lived. Dinosaurs are around and supernovae decide to do some other thing. Okay, who knows? Or high redshift solutions like scalar fields prior to recombination and all that. That doesn't. But at low redshift, if you think you can change expansion history of low redshift, even an arbitrary change in expansion history cannot fit the data with a Hubble, with a Schur's measurement.
Okay. Thank you. Is there any questions?
Yeah, there's a hand
Hi,
up.
Shibang, it's Alessandra. Hi, Dragan.
Hi.
Managed to join eventually. Wonderful talk. Thank you. So you say if it's true, we should get the Phi Sigma soon. Still is like squeezing information out of DESI, or you think we need something else?
Still
like
squeezing information.
Point.
Yeah, still squeezing information out of DESI. And Alessandra, it's funny because after I started giving talks on these results, everyone started asking, when are you going to have 5 sigma? And I don't know, because these forecasts are very uncertain. They depend, and it requires actually a lot of work to do forecasts, as anyone in Euclid probably knows. So we scrambled to find out. We had an exchange on Slack. When are we going to have 5 sigma? Because it could come from different corners. Of course, year 5 BAO data, but we have full shape data that for for DR2 we haven't finished full shape. But full shape has more information, but many more nuisance parameters. There are 42 nuisance parameters in the DR1 full shape analysis. Then we have the bispectrum coming around, and even other probes. Who knows if they will help? Maybe. So there's a lot of uncertainty, but just from the BAO, DR3 year 5, I would guess we would have 5 sigma, but I mean, pretty surely there would be 5 sigma from a combination of these things just from DESI, DESI and CMB of supernova, I mean.
Thanks.
Okay, if there is no more questions, so let's thank the speaker again, and thank you very much for the talk.
Thank you, everyone. Thank you. It's been a pleasure talking. Best of luck with your future talks and activities. Thank you all.
Thank you, Dragan. Thank you very much.
Yeah.